Welcome. We will talk about object detection now. First of all, I will introduce what object detection means in comparison with image classification, and then move on to the classical object detectors that have been there. Of course, that use convolutional neural networks. Then after that, to talk about some recent object detectors, especially YOLO. So now, when you want to classify an image, we run it through a convolutional neural network like AlexNet or something, and then we get some vector, maybe 4096 dimensional, and we fully connect that to a 1000 dimensional vector. Why? Because there are 1000 classes, and for each of these classes, it will give a probability. So therefore, the highest probability class is the class of this image. That is the image classification. So it is a label per class. But there is only one paradigm. There's no spatial extent that is considered here. But then there is something called semantic segmentation, where each pixel has to be labeled as grass, cat, sky, and so on. So no object, but just pixels. But in object detection, we want to draw a box around each object and give it a label. So dog, a dog, and cat. Individual objects are individually identified and bounding boxes are drawn in object detections. But here also you have multiple boxes, multiple objects, and you can combine object detection and semantic segmentation, and we can have instance segmentation where the pixels are labeled properly belonging to each of the object, each of the instances. So you can see the two dogs have been differently labeled. Yes. Given a single input image, object detection means a set of detected objects must be output. For each of the objects, we have to predict the category label like dog, dog, cat, and so on. And also from a fixed set of categories actually. And also the bounding boxes X, Y, width, and height have to be predicted. Yeah. So when multiple outputs are there, no need to output the variable number of objects per image. Now the challenge is we need to output multiple outputs. So multiple types of outputs are there: class name as well as the width, height, and the location. So we need large images, maybe 800 by 600. So now let's see how to detect a single object. So trees localization as a regression problem. We see what that means. So you run it through some CNN, open pre-trained on ImageNet, and then we get 1094 vector, and that vector we classify into one of the classes. That's fine. And then what we do is we get the fully connected network to produce four numbers. Those four numbers are the height, width, x, y, and the width and the height. Remember, we have the ground truth box in object detection. Some person annotated that, and then we can compute a loss between the annotated box and the box that the model predicted. So this is a so-called a regression loss because that finds the difference between x and x prime, y and y prime, W and W prime, and H and H prime. So those two losses are combined in using some scheme to come up with the final multitask loss. This is detecting a single object paradigm, but this is not useful because images can have more than one object. So this one is okay. We have to predict cat, X, Y, W, H. Four numbers have to be predicted. If you have three objects here, dog, 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 we have to say dog, bounding box, dog, bounding box, cat, bounding box, 12 numbers. But when you have large number of objects, then so many have to be predicted. So this is not something that can be done with this paradigm. So one way of is this so-called sliding window approach, where you try to locate a varying size windows or bounding boxes at every single location of the image and try to classify them. So dog or not, we put a bounding box, and this the blue one is the bounding box. We just think that this is a good bounding box, and then we say cat, dog, or background, and then we put it there. I put it there, put it there. But how can you find these putative places? How many possible boxes are there in an image of size X and W? So many of them, right? Consider box of size small h times small w. So possible x positions are w minus x plus 1. Anywhere it can be kept. Height positions h minus h plus 1. possible positions are these, and there can be different sizes also. Total possible boxes, it turns out to be this much. So it's a massive number. For an 800 by 600 image, 15 million boxes. You can never finish computing this. So therefore, sliding window approach is not correct for this. So therefore, people came up with this so-called region proposal approach using a classical network, and that classical network is called selective search. What that can do is that can just look at this image, and using a conventional approach, that means not a deep learning approach, it can give you, okay, there can be a box object here, there can be object in this box, there can be an object in this box, and so on. So they give about 2000 such boxes per image. So from 58 million you reduce it to 2000. This is a good thing, right? So this is called selective search. So and one of the early contributions is by Ross Gershik and others. This region proposals plus CNNs, this is called RCNN. So you know about CNNs now. What you have to do is to run a CNN on each of these proposals. So therefore, you locate these proposals on the image, and we said that using, if you selective search, you get about 2000 proposals per image. And on each of them, we warp each of them to 224 by 224. You saw that earlier in our ResNet fine tuning, we had to do that. And then we run the convolutional neural network in each of those, on each of those warped images. How many times the CNN has to be run? 2000 times, because there are about 2000 region proposals. And on the features that are computed using the CNN, we apply a support vector machine that can classify into the classes, and we do the so-called bounding box regression to compute the four numbers. Actually, they are called, they are not exactly those numbers, but something related to that, height, width, x, and w. So that relationship is here, but I will not talk about that too much. So in test time, we input the single RGB image, we run the region proposals to get the 1000 regions, 2000 regions, resize each region to 224 by 224, and run independently through the CNN to predict the class scores. Use the scores to select the subset of region proposals to output. Many choices are there: threshold on background, low per category, or top K proposals by image, and then compare with the ground truth box. So this is what RCNN means. Yes. Any questions about how RCNN runs?
So normally I notice this is used more in video-based detection. Is there any reason for that? Like for traffic monitoring different vehicles in traffic, or animals, or other movements of people?
You can run an object detection on videos. It is a usual thing to do. So then they will consider each frame as an image and run object detector on them. That's the
Okay,
usual thing that they do. There is no
this,
information transfer from one image to the next.
and this self-driving vehicles also use this similar technology, or not this kind of thing where they have several
They have to
cameras and
do object detection, but definitely they have their own proprietary object detectors, I think.
Okay, sir.
Not these that we described. But they do run object detector. They have. But I think they have their own, because they have large data sets, daytime, nighttime, this and so on, right? So at any time they have to be able to detect the persons, right? So the company secrets, actually we don't know. But definitely they need the object detectors.
These CCTV cameras also, they can count number of people and things like that.
Yes. Yeah.
That's also like this, is it? RCNN or?
Object detector. Actually, RCNN is not used. It's an old one now. People usually use YOLO now. So I will describe about that later.
Okay, sir.
This one is a 2015 contribution. So this one also changed. But even after changing, this is too computation heavy. Yeah. So we look at those, the changes that they did. So before that, how do you measure the goodness of an object detector? So to measure that, we have to see this our predicted box, how well it overlaps with the ground truth box, right? So here you can see an overlap of about 50%. How can you compute that intersection over union? You can get the area of intersection in light blue. You can see the area of intersection, and you can divide by the area of the union, right? That's a good measure, right? So this, if this is 1, it's a perfect detection. If this is greater than 0.5, it's a decent one. So 0.7, a very good one. 0.9, an almost perfect detection. So IOU, or intersection over union, or Jackass index, is required to evaluate the goodness of an object detector. But it's slightly more complicated than that. So average precision and so on are required, but I will not talk about too much of them. Average precision measures how well a detector makes prediction. It is the area under the precision recall curve for one class. So I will not go into details about this, but average precision is what they use, and mean average precision means they average this average precisions over all the classes: human class, pedestrian class, car class, bus class, and so on. So mean average precision. So you have to say MAP. So to compute MAP, how much IOU do they need? Maybe usually 0.5. So sometimes they would say MAP, MAP, and they will write 0.5 here to show that with IOU of 0.5, they have come up with that MAP score. So this COCO protocol, Microsoft COCO dataset, they did not have AP50. They had all sorts of them. So starting from 0.5 to 0.95. So the COCO one is much more advanced. This is how you detect them. So evaluating object detectors, to compute the mean average precision, we run the detector on all images with NMS. NMS, non-maximal suppression. If you have two co-located objects, you don't consider both of them. You consider the best one. For each category, compute the average precision under the precision recall curve. For each detection, highest score or lowest score. Otherwise, mark it as a negative. Um, and plot a point in the PR curve. So I will not go through this process in detail. Mean average precision, average precision over each category. So for COCO, we have to compute the MAP at all these thresholds, and COCO MAP is a different one. Otherwise, you specify a number, IOU number. Yeah, that's how you do this. So this is the RCNN that we saw. This problem is very slow because we had to run 2000 forward passes on these 2000 regions that the region proposal network would detect. It is a classic region proposal network. So solution, run CNN before warping. So you can see this is the original network that we looked at, so-called RCNN. So selective search followed by CNNs. But in the new one called fast RCNN, you run the CNN and then locate the selective search regions on top of the feature map. See, we locate the region proposal regions on top of the feature map. So you have to just run the CNN only once and extract the features on top of that. So then computation load drastically reduced. So then there's a thing called ROI pooling. You have to take the features that are in the box. So that's called ROI pooling, has to be done. Then on each of these regions, you run a small per region network to compute the bounding box and the plan. This is called fast RCNN. It's a great advancement from RCNN. Okay, so you can see the most of the computation happens in the CNN, and that happens only once. And the per region network is a relatively light network. So, for example, you can use the AlexNet for that, or SNet as a backbone. So cropping these features is called ROI pooling. So you can see a bounding box located on the image, and after the CNN, we locate the bounding box on the feature map. So you can see it does not snap to grid. So you have to make it snap to the grid, and then after that, divide the grid into 2 by 2 grid, roughly equal neighbors, and then extract the features from those. So region features always the same size, even if the input regions have different sizes. So problem, slight misalignment due to the snapping, different size regions, this weird. So this is a problem with this ROI pooling thing. So here's a little animation of how ROI pooling is done. So you divide the into a sort of a 2 by 2 thing, and then get the maximum value of this. Okay, so fast RCNN versus slow RCNN. Okay, but this also had problems. Now, when they evaluated this again, so see, this is how researchers come up with ideas, right? Mr. Malapat asked, like, how do they research? These people come up with ideas? So they evaluate existing work and see, look for problems that need improvement, and they seriously needed some improvement. So when you think about training time, RCNN had 84 hours of training, and fast RCNN only 9 hours of training. That's good. But when you think about the testing time, RCNN had 47 seconds for excluding region proposals. With the region proposal network, 49. No much difference. So people did not care, only 2 seconds difference. But if you take the fast RCNN, the faster version, including region proposals 2.3 seconds, excluding region proposals 0.32 seconds. Now you can see region proposals take so much percentage time. So they wanted to get rid of that region proposal network, also called selective search, that was based on a conventional technique. So for that, what they did was they said, okay, on these feature map, we will run a region proposal network also. That is also a deep learning based one. So this conventional regional proposal thing, you don't you don't run. So region proposal network (RPN) to predict the proposals from the features. The proposals also are predicted using this deep learning based features. Otherwise, the same as fast RCNN. Crop features for each proposal and classify each one of them. Classification loss, bounding box loss, and then classification loss, bounding box loss. So they have some kind of a training curriculum or something. You do this first, you do this next, and so on. So we will not go into that detail. So if you like, you can look at this. But fast RCNN, learnable region proposals, jointly trained with four losses: RPN classification, anchor box. Uh, uh, Anchor box is object, not an object. So that is the uh, so they have so-called anchor boxes. It's has an object, not has an object, according to what the network says. RPN regression predict the transform from the anchor box to the proposal box. And object classification classify proposals as background object class. Object regression predict the transfer from the proposal box to object box. I think this is too much detail for you to be described that in a short time, but you can think that there are so many components in the loss because this is a complicated exercise. The object detectors are very complicated and cumbersome actually. So now you can see test time speeds of fast RCNN just from 49 seconds of RCNN became just 0.2 seconds. But still, this is not real time, right? It takes 0.2 seconds. That's too much actually. So fast RCN is a two-stage object detector because we run one per image backbone network and they get the region proposal. Second, run one per region, crop the features, ROI full overline, predict the box class, predict the bounding box offset. Because of these two processes, these are called two-stage detectors. Two-stage detectors. Why do we really need the second stage? They asked again. So with that, they came up with the so-called single-stage detectors. In the single-stage detector, you detect features and you locate putative bounding boxes like that, different shapes, and on each of them, they are called anchor boxes. They ran classifying the anchor and then the box transformation. So remember key anchors at each position in image feature map. So see, this is what they did. So 20 times 15 such anchor boxes, and at each location, you can have in this case three anchor boxes, right? Three anchor boxes here, and for each of them, you predict the class or the background. So how many class, like cat class, dog class, and so on. So this is a single stage detector. So RPN classify each anchor as an object or not. A single stage detector classify each box as one of C categories or background. So this is a faster one, but slightly less accurate. Sometimes use category specific regression also. So we will not talk about that. That's okay. So when you think about all these set of object detectors, before we move into YOLO, you can see the GPU time, time spent on the graphics processing unit. And then you can see the overall mean average precision. So you can see the inception based net, ResNet, inception V2, inception ResNet, inception V3, mobile nets, ResNet 101, VGG. I think you understand most of these networks. And here they have written fast RCN based ones, RFCN based ones. I don't know what that is. I don't remember actually. I should. SSD single shot detectors. So you can see if you take these diamonds, those are single shot detectors. If you take diamonds, they have usually overall MAP is low, but they are very fast. Very fast, the overall MAP is low. If you take Inception, ResNet, and so on, their GPU time, the computation is high, and the accuracy is also high. This kind of trade-off is there. So key takeaways, two-stage methods, faster RCN gets the best accuracy but are slower. A single-stage method, SSD are much faster but don't perform as well. Bigger backbones improve performance but are slower. Diminishing returns are slower method. So then there were many things that were introduced. We don't even discuss about them. So many advancements are there in object detection. So if you want to use TensorFlow, you can follow this, and if you're using PyTorch, you can use Detectron for object detection. Yeah. So in summary, so RCNN was first introduced, and then fast RCNN means you switch the convolution neural network and the selective search process, right? So that's the fast RCNN. But still, the selective search had to be applied, and region proposals had to be located on the feature map. But in the faster RCNN, those region proposals are also computed from the feature map of the convolutional neural network. And in single stage detectors, they are fully convolutional detectors. They do not need the region proposals. They directly predict the classification loss and the bounding boxes by using this, slightly changing these anchor boxes. Okay. Any questions about the object detection up to now?
So if you have to decide between the Google library and the Facebook one, which one is better to go for
That is a good
research?
question. The question is whether you want to go with TensorFlow or with PyTorch, right?
Correct.
Now people don't have to use TensorFlow that much. People they use PyTorch.
Okay, thank you,
I
sir.
also have switched to PyTorch. You can see that the code that I use, import torch, right? That is using PyTorch. I did not import TensorFlow
Yeah.
because the whole community moved to PyTorch somehow.
Is there any reason for that? It's better or they're both
There
development,
is
isn't it?
there is a reason. I don't remember the reason actually.
I'll search it, sir. Thank you.
There's a very valid reason. Okay.
Because I was looking at one book, sir, deep learning or something by it's for Keras, which is running, I think, on top of
TensorFlow, yeah.
and so now only thing is, but I think in that latest book he's covering both. I
Who's
can't
this
remember
person?
his name. He's a French scientist, computer
Hmm.
scientist. I can't remember his name.
Uh,
I'll check and let you know, sir.
yeah. Okay, so now let's look at single stage detectors because these are important. To remind you again the difference, in the faster RCNN, we compute the convolutional feature map of the entire image, and we run the so-called region proposal networks, and you get these region proposal boxes. And from these boxes, you do ROI pooling. What that means is the features are collected for each of these boxes, and then we have the ROI features, and then on top of them, we run the detection. That means the classification and the regression. Classification means to say that box is cat, dog, class, or car, or whatever. Regression means to slightly adjust the bounding boxes. But when you take single stage detectors, you just have the convolutional feature map of the entire image, like so, and then you run classification and regression on top of that and to get the detection. So you can see it must be very fast, but of course the accuracy will drop because of this direct computation. All right. So YOLO is one of those very important contributions in this area. So we will briefly study about YOLO and exactly understand what kind of ground truth is required to produce YOLO. And I will run YOLO and see, and it's a 5 minute task to run YOLO now. Okay. Any questions before we get into YOLO?
So the name of that author is Francis Chollet. I'm not sure whether I'm spelling the name correctly. Francis Chollet. Deep Learning with Python third edition. It was recently released quite recently, about a few months back. Third edition. I shared it in the chat, sir.
Yeah, okay. Um, this book, right?
Yes, sir. It's supposed to be like a very good, especially for beginners. It's a very good book.
Because it's a good book. Yeah.
There are a lot of
Yeah.
good French people who are deep by this study, this deep learning and stuff.
Mm.
You haven't come across his books, sir?
I have not come across this book, and it talks about all this, right? The Keras,
Yeah, I think
control.
he's the inventor of that Keras. I think Keras was running on top of that Google Frame.
TensorFlow, yes.
At intro, and then later, yeah. So I think to make it easy or something, and then he sort of got into that
Yeah.
area. I have the off copy if you want. I can have it with you.
Yeah, please do share it. Yeah, yeah.
Okay, sir.
Very useful.
It's quite recent, actually.
Mm. The thing about these areas is initially getting into the area is hard, but after you getting into it, everything sort of becomes clear to you. So you just have to read a book, start one or two chapters, and start coding. Then everything becomes clear to you.
That's true. That's true. So, except only problem is the GPU is a bit expensive. That's the only sometimes we get stuck with that area.
Okay, if you need access to a GPU, I can give you access to a GPU.
Okay, sir. I'll let you know. Thank you.
So access means you can remotely connect to the GPU machine.
Okay, sir.
Okay. And okay, now let's get into YOLO. Thank you for these comments and the book. So in YOLO, the meaning is you only look once. Okay. So it's by Joseph Redmond, and after that, other people started producing papers called YOLOs. Now it has been taken over by a company called Ultralytics. So divide the image into S by S grids. Usually it's SA7. If the center of an object falls into the grid cell, that grid cell is responsible for detecting that object. Okay. Yeah. So each grid cell predicts B bounding boxes. Okay. And the confidence scores of those bounding boxes, CI, probability of an object being there, and multiplied by the IOU between the ground truth and the prediction, reflects how confident the model is that the box contains an object, and also how accurate it thinks the box that is predict. Each bounding box consists of 15 predictions, 5 predictions, X, Y, W, and H, and the confidence of that. Yeah. So XY is the center of the box relative to the bounding box bit cell. I will explain that in detail later. WH is the width and height relative to the whole image. Confidence, intersection or union between the prediction box and the ground truth box. So each bit cell also predicts C conditional class probabilities. So given that there is an object, probability of cat, probability of dog, and so on. So if you have that many classes, C classes, it will produce C numbers. So P probability of class I given object is probability multiplied by probability object. times IOU truth prediction. So that is probability of class times IOU ground truth and prediction. Predictions predicts one set of class probabilities per grid cell, regardless of the number of boxes. Output tensor shape, that is very important. The shape of the output tensor, S times S times B times 5 times C plus C. What is S times S? So here you can see how they have divided. They are divided to S times S, 1, 2, 3, 4, 5, 6, 7. 7 times 7, right? You can see the image has been divided to 7 times 7. And in each of those, they locate how many bounding boxes? Usually two bounding boxes they locate, two shapes they locate. And why do we have 5? For each of the bounding boxes, they have this confidence X, Y, W, and H. So that many parameters. And for each of the classes, each of the grid cells, they will predict a class probability. Yeah. So regardless of the bounding boxes. Yeah. So you can see the grids are there, and then you can see the bounding boxes and confidences. So confidences, they are showing by the thickness of the line. So here it's very confident that there is an object, right? Can you see that here? It is very confident, the thick lines. And then these are the class probability maps, and based on that, you are able to get these thick ones and call which class it is based on the center. So this is what YOLO does. Okay, in more detail, take the convolution feature maps at 7 by 7 resolution. Okay, 7 by 7 resolution. That's why we say that the image has been divided into 7 by 7 grid, 7 by 7 resolution. You can see that, right? And at two fully connected layers to predict each location, a score for each class, and two bounding box confidence. For Pascal, this is the dataset Pascal VOC, 7 by 7 grid times 30. How do you get with 30? 20 classes, right? 20 classes. These actually C. These your B, like how many bounding boxes do they need? And of course, we saw how we got this 5, right? X, Y, W, H, and 1 for the confidence. So you can see the tensor size that it gives is 7 by 7 times 30. Can you see that 7 by 7 times 30 here? So this is what. So now, if the output of the network is 7 by 7 times 30, how do you compute the loss? You from ground truth data, you must construct a tensor of that size, right? Okay. So in more detail, in your algorithm, if you use 7 by 7 cells and there are 20 classes, for each training image, what will the ground truth tensor look like? That's a question I'm asking. Okay, here's the answer. Input image is divided into S by S grid. Here S is 7. So the grid has 49 cells. I mean, that is clear for you. Oh, sorry. And each grid cell is responsible for predicting objects whose center falls inside that cell. For each cell, YOLO predicts X, Y, WH, and XY is the relative to the cell, and WH is relative to the image. That I will show you later. And the confidence score, a probability that the box contains an object times IOU with ground truth, and class probability distribution over all C classes. Here C is equal to 20. So for YOLO V1, this is the original version you're talking about, each cell predicts B bounding boxes. Here we use B equals 2. So you can see because the two bounding boxes, 2 times 5 parameters, x1, y1, w1, h1, c1, x2, w2, y2, w2, h2, c2. These are the class probabilities and the location and the height and width. And then these are the 20 P's, 20 probabilities for each of the 20 classes. So you can see this is how you get the size 10, 30. That is 5b times c is 30 number per cell. So that's how the ground truth tensor should be 7 by 7 times 30. I hope this is clear to you. Okay, in more detail. Okay, let's consider this example. Now here is an image. This image has 3 classes, right? Three classes are what? The dog can be there, the cat can be there, and the tree. Those are the three classes that we consider. So therefore, there will be not 20 classes here, but only three classes, right? Three classes. So I have given, and I decided to have only one bounding box, not two bounding boxes, just one. So B is equal to 1. So, and these are the class probabilities. Can you see P cat, P dog, and P tree? Okay. So now what we do is uh, there's some bounding box here. You can see this is the ground truth bounding box um, here. So you can see the probability of an object being there we take as 1 because there's a object center. The center of the cat falls here, right? Center of the cat is here. You can see that center of the cat is here. So the probability of that containing object is 1. And then these numbers, how do you get these numbers? X and Y and the width and the height. X and Y relative to this corner, okay? Width and height relative to the image. So here is 0, 0. Here is 1, 1. So I thought that this cross lies about uh, 0.7 in vertically downward direction and about zero point 0.8 horizontally rightward direction. So that's why 0.7 and 0.8 is 0.7 and is 0.8. And then the size of the object relative to the image. So you can see height is about this much, right? Height is about this much. So it is about 0.3, right? One sort of 1/3 or some. Okay, it is about 0.4, little smaller than half. So that I thought it's 0.4 or something. So that's why this 0.4, and then 3 is this much. This one, it is like 1/3 of that. That's why you have 0.3. And cat probability must be 1 because it's the cat, and all other two probabilities are 0 because this is the ground truth vector. Ground truth vector for that cell, for that grid cell. And each of these cells will have a ground truth vector. So let's take another one. In this one, there's no object. So therefore, this probability is 0 here. So none of these other parameters are now put there, or nothing. And if you take the dog box case, it's 1. So you can see 0.9, 0.3 because of this center being here. And the dog is slightly large, 0.44, 0.49. And the dog probability is 1. The dog probability is 1. So this way, you compute the ground truth sensor of this size. 7 times 7 times 8 for this example. Any questions about it? Okay. We'll briefly talk about the YOLO's loss. Yeah, it's a very complicated loss. First of all, you have the regression loss in the YOLO. Remember, it's a single stage detector, so all these losses will have to be computed that one. You can see depending on the location xi versus the estimated one, ground truth versus estimated one. You square them, and if there's a difference, you can see it is penalized, right? And it happens only if there's an object. This is an indicator function to see whether there's an object or not. So you do that for all the cells, all the 49 cells, and all the boxes. For all the cells and all the boxes, if there is an object there, we try to make the predicted width and the ground truth width also the same, and you get the square root. There's a reason for that. Then for all the bounding boxes and all the cells, if there's an object, we object or no object confidence we calculate. And for no object ones also, we calculate the no object one. There's a reason for that. If you're interested, please look at the paper. And now for all the cells, boxes are not considered. Boxes are not considered here. If there is an object, we find the class condition, class prediction. So these are probabilities of the predicted classes, all the 20 classes. These are the ground truth classes. Only one will be one there in the ground truth. So this is the loss function of YOLO.
So in layman terms, how would you define a loss function? Is it like the total amount of loss in a image, or
Loss means actually error. It's actually error, right? Now the ground truth location is, let's say, 0.7, okay? X is 0.7 and Y is, let's say, 0.8 for the time being. And now network predicts 0.4 here and 0.3 here or something. There's a difference now. So you subtract and square it. So if that, so long as this is not zero, the network will try to adjust the parameters to reduce that. That's how the loss works. And on top of that, remember, on this loss we calculate the gradient, right? Gradient. So those gradients will make the weights go down or up to make this loss small.
okay, sir.
Make this loss small, or not only for one image, but all the images that we have in the data set. That's why you have to keep on running the network multiple times to reduce the loss. And then the network weights will have been trained when we run multiple. So remember, in our example that we did, we ran the network for how many epochs? We ran it for 24 epochs, right? 24 times we ran the whole data set through the image. And there our loss was just the wrong class, right? If the class is Nanjan, if it predicts Scarlet, it's wrong. So that you penalize, it's wrong. So for that you can use the cross entropy loss. But here you cannot use that. We had used these kind of losses. So depending on the situation, we come up with a loss function.
Thank you, sir.
Thank you very much for that question. So this is an important one. So cell 1I contains object, predictor J is responsible for it. So small deviation matters less for large boxes than for small boxes. That's why they get the square root. Confidence of the object, confidence of no object. Downweigh the loss from boxes that don't contain objects, no object 0.5, and then class probability. Yeah. So when you think about your resource, each grid cell predicts only two boxes and can only have one class. This limits the number of nearby objects that can be detected. Poor at handling the aspect ratios and scales. So because there are 49 cells and each cell can have two boxes, it can only predict 98 objects. YOLO can predict only 98 objects. That limitation is there. Grid, hard to detect small objects, limits total number of objects to detectable due to the less precise bounding box regression, results in localization errors. Localization accuracy suffers from compared to fast RCNN due to coarse features. Errors on small boxes. 7 times speed up though, because it's much faster, because you don't have to have two stages. So you will run at 45 frames a second or so on, versus 7, 8 frames a second. But correct ones are 65%, and here correct is 71%, and localization errors are large. The reason is YOLO has coarse bounding boxes. Yeah. Okay, so before getting into some other one or two networks, I will show after this, not all of them. We will run YOLO. It's very easy, okay? Very easy. So let me put a mark down here, YOLO. I'll put a thing here. So, that's what we did. Okay. In YOLO, you only look once. Okay, it's very easy. Import torch, and then the model is torch dot hub dot load. So we can see ultratext YOLO V1 or 5 or something, pre-trained true. That's it. That's it. So then images. So you can get the images also. So that we can get those images, but there is an image that they have given. Let's use that one. Also we can use. I hope. Yeah. Okay, then we just use one for now. We can give batch of images though, and so this image of Zidane, Zidane results model. You run the model and print the output, and you can save the results or show the results. So just show, and we can get the tensor results dot x y x y 0, and it's done that. This problem, no module call name Ultralytics. So Ultralytics, no module name Ultralytics. So you have to install that. Mm, you can search for that kind of thing in that GPT or your favorite, or you can use AI. It will tell you how to install. Pip install Ultralytics. So CMD. I always use command prompt to install, but you don't have to actually. Of course, you have to activate your environment and then say pip install Ultralytics. Okay, let's try this now. Some other requirements. Really, I think I did this. Did something to this. Okay, so we have restart the runtime now. So let's do that. You can see that person, cell phone, Thai, person. You see that. So it's very, very good, right? Very good. Then it tells you person type and the bound box coordinates the explanation, all these things. So it's so simple actually to run YOLO, as you can see. Mm, Also, you can run it on your own images also. Um, mm, you can
So
upload
the
another picture.
so the
Sorry,
mouth was detected as a phone, is it, sir? The
is
picture?
it a? It's a mistake, right? Yes, yes.
Why was that? Because of
Uh,
the shape
I don't know,
or
but the confidence is 0.27, right?
0.27?
Yeah, I don't know why. We throw it like a one. So the accuracy is low anyway, YOLO. But remember that we are using YOLO 5. There are more later versions of that. So mm,
Does it is there any specific thing that it will detect, like person? Then is there a list of things that we know that it can detect?
I think it has been the YOLO V5 has been trained on what? Let's look at that.
So what's the connection between this Ultralytics and YOLO 5?
I think that company started working on YOLO like works, and now they have the leadership in that. So all the people use their work, their models now.
It's like a API maybe to the YOLO 5. Yeah,
Not
it's
the
sort of
API, they have the weights also. See this.
so it's part of that. Okay.
Yeah, everything is there. So you just download. How many? What are the classes? I don't know. I think you have to ask ChatGPT.
There's a models dot names. I think you can run that command. It will give you the classes
Ah,
names. Try
yeah,
that.
yeah. Ah, so these regular ones, right? Yeah.
Names.
Model dot names,
There's a S, I think, sir.
names
Yes, sir.
like this.
Try that and yeah, try that and there is no bracket, sir. Yeah.
Yeah, yeah. So 80 classes, right?
Okay. Thank you, sir.
80 classes.
7.
Yeah, thank you very much. Thank you
80.
very much for that. Yeah, I did not know that 80 classes. That's why they don't even say it. I mean, it's very obvious.
Okay. Different
There are
types of animals. Animals, mainly animals, sir. Right? Animals, and then yeah,
bicycle, car, motorbicycle, airplane,
motorbike.
bus, truck. Yeah, so many things are there. Traffic lights. Yeah,
Maybe toothbrush also.
hygiene,
Okay.
toothbrush, cow, race, steam, knife, refrigerator, toothbrush. All these things are there. Now it's good to see the other models in Ultralytics also. So Ultralytics, they have Euro V26 is there now. Euro 26. So they are later models and using advanced techniques than what we discussed here in the slides. So some of these are there in the latter models. Um, so real-time object detection and image segmentation. It's a second segment also. It's built on deep learning computation advancements and whatever. Yeah, I mean, anyway, let's not try to read it. I don't have too much knowledge about it. So you can ask ChatGPT what are the advancements in YOLO V6 and so on, V26 and so on. I just want to show you that this can be done. It's so easy to get this done. You can put your own image also and get this detected. And you can, as you asked earlier, if you are getting a video, you can feed every frame to this, then it will do detection in every frame. So that will be much faster, much nicer. It's like detecting things on the video. Yeah. That's your object detection. So let's look at the slides and briefly study about other things. This one is called SSD, predict boxes of different sizes from different con maps. So there are different con maps, and you can see from each of these con maps they detect. So as a result, they can do different sizes, I think. So yeah, with different sizes of objects. So mean average vision is high, as you can see. Of course, YOLO has also advanced. So I had some details about this, but let's ignore that. And then what they do with the bounding boxes. So they have more bounding boxes than we looked at in YOLO, but I'm sure that YOLO later versions have more bounding boxes than the two bounding boxes that we discussed. Uh, yeah, other detectors. So there's a thing called coordinate. Now this is a different detection paradigm than these anchor box based ones. There you take the image and then they have this thing called a coordinate, and that has two heat maps. First of all, top left corners and bottom right corners. So top left corners, bottom right corners, they join and then they have an object. That's how they come up with this detector. So no anchor boxes. The corners are directly predicted. This is what that is. Detects a pair of corners of a bounding box and groups them to form final detected objects. So to grouping, they have something. We detect an object as a pair of bounding boxes. Corners grouped together. A convolutional network outputs a heat map of for all top left corners, a heat map for all bottom right corners, and an embedding vector for each detected corner. The network is trained to predict similar embeddings for corners that belong to the same object. If you think about the coordinate slightly more detailed, so if you take this, for example, you can see the horses and riders are there, and this so-called hourglass network is there, so it predicts top left corners and the bottom right corners. They will predict heat maps, embeddings, and offsets. So you can see these predicted one heat maps. So then you have to do some corner pooling thing. That means you have to pair the top left corner with the bottom right corner. Then, because of the often there is no local evidence to determine the location of the bounding box, we address this issue by proposing a new type of pooling layer. They have some thing called pooling layer. So you have the feature maps and top left corner pooling and its output. So I don't understand this too much actually. I didn't study this, but you can see the general idea of that. So it's a 2018 version. Then detection transformer is a very good one. It's a 2021. It's a transformer-based network. So there's a CNN to reduce the feature size. I think then the transformer network is there. Good thing about the transformer is it can attend from one place to the other. So detections are better. So backbone, so in code is there. So transformer decode is there. So they will predict the class box numbers, no object thing, class box, no object thing for each of the predict object. There are a thing called object queries. Each of the object queries they will predict this. So about this paper also, my knowledge is very limited, so I cannot give you detailed description of that. But knowing this name is important. Yeah, those are the things that we wanted to cover about object detection. I have prepared a quiz also. Please do that. It's directly based on the slides. object detection quiz. You have time until 11:59. So we can do some of the questions now. So how many numbers are needed to specify bounding box in object detection? How many numbers? X, Y, W, and H, right? So 4 numbers are required, like that. What is the role of non-max suppression in detection pipeline? Because when close by bounding boxes are there, you have to remove them. So that's done by non-max selecting backbone architecture, improving the gradient flow, creating the task probabilities, eliminating redundant overlapping detections. Okay, right. Next one. What is the first step in RCNN at test time? Predict the final object categories directly. Use fully connected layers without the CNN. Crop the size each region proposal. Apply non-max suppression. Compute IOU ground truth. I don't remember that now. So if that is the case, please go to the slide and look at what it says. RCNN and runtime. Run region proposals. Test time. Resize each region to 224, 224. Yeah, so crop and resize region proposal. Like that. What is the RCNN computation slow? Requires pixel level annotations, cannot use pre-trained models. It contains IOV. It requires CNN forward region. Yeah, CNN for each region, right? Like that. So you can see the quiz is not difficult. They are directly from the slides. Please do this quiz and complete. Yes. Under object detection, so you can see what we covered is the what we understood what object detection means. That means you need the class label plus a bounding box coordinates. And we looked at the 3 early object detection iterations: RCNN, fast RCNN, faster RCNN. Then we looked at YOLO and we looked at YOLO's ground truth and some anchor-free object detectors like CenterNet, CornerNet. There's a thing called CenterNet also, and so on. So that's all for today. If you have any questions, I can answer. Otherwise, you can log off. We are done for now. So the plan for the next class is I will hopefully do some questions so that it will be easy for you to answer the exam. That's the plan for next time. But of course, I can do advanced, slightly advanced, recent or not advanced, recent topics like vision language models if you want, or image generation through diffusion model. If you like, I can do those also. Otherwise, the general things that we need to cover have been covered. We can do some questions next time.
Good evening, sir.
Yes.
Sir, quiz number 8, it was opened in April 15. Can you reopen that one? Because we couldn't attend that one.
The quizzes are there to, if you attend the class, you can do it. So I will not take all the quizzes. I will take best 80% or something like that. Don't worry about this. Yeah, so if you do 5 quizzes, 6 quizzes out of 9, that's okay. You get close to 90, no? It's okay.
Yeah.
Okay, yeah, that's okay. And what I do for these quizzes is I take the slides, upload into ChatGPT and ask it to make questions. So it makes exactly questions that are there from the slides, nothing serious actually. Any other questions or comments? How many quizzes have you done?
So I also missed like 3 because I didn't get any. It was my fault. I didn't check the model and there was no sort of notification. So I missed like that 3. Then later I just realized that I had missed around 3 because I think what happened was I think it was uploaded, but there was no sort of notification that there's a quiz on the site, sir.
Okay. So quiz number 8 you had to open?
I had about 3 some I missed myself, I think.
Then the last one I'll open. I don't worry about it too much. I think doing them again is also trouble. I think you have to go this conclusion. It's important one, so I'll open that. Up until today. Yeah, it's very fair to open that. I think the deadline is very old. So until tomorrow night, I hope. Yeah. That's okay, right? If you get lower marks, let me know. I think I can adjust something for quizzes.
Thank you.
Because anyway, I will get best 6 out of 9 or something like that. So next time also I'll give one, and then it's okay. Maybe I'll open this also, then it's okay, 16 people have. Oh my goodness. Only 2 or 3 people come to the class and 16 people have attended. Yeah, they will they'll find the exam very difficult because we will give questions slightly more practical at the exam. Please send them a message to attend the next class so that I can do some questions and they can get some practice for the exam. So I open 2 cases. I think that's okay. So any other comments or questions? Question?
Can you share some past papers or maybe do you have any?
Yes, yes. I will upload some past papers.
Okay, sir. Thank you.
I had 3 past papers. I uploaded those.
Thank you, sir. So is it possible to fund that 4, 5, and 6 in the quiz? I think I missed those 3 bits.
I'll open one more. If that's okay. That's okay, right?
Okay, sir.
Yeah. Don't worry about it too much. But this is also trouble, like that means you have to go through the slides and do it. Otherwise, you won't be able to at once answer this, I think.
That's not a problem, sir. So here, what happened was I didn't know that it was there, so what a mistake.
Give one more day, otherwise you won't have time. Okay.
Thank you, sir.
Anything else? Are we okay? Okay then. You may log off, but thank you very much for joining. Have a pleasant rest of the Saturday.
Thank you, sir.
Thank you.